I'm feeling good this time. I feel like I can find it this time.
Can I do the lab instead?
I can't force you to do this, so if you would get more out of doing the lab than you would, or you're more constrained on time, you can do that. But I do want to go over how to solve these kinds of problems so that we get some experience with that, just because I think that it's a big weakness in the early classes in the program and really in the program as a whole. So I want to be able to do that. So this problem is basically saying we have a reasonably large triangle and we want to find the path from the top of the triangle to the bottom of the triangle that has the maximum path sum. So in the small example up there, 3 plus 7 plus 4 plus 9 is the largest sum you can get by going either diagonally down left or diagonally down right from any particular position starting at the top of the triangle. So if we read this in, we need some way of figuring out and storing these values. What structure makes the most sense for this? We need some way to represent this internally.
We've gone over it so many times.
I don't know, isn't this like what my pictures of what?
Yeah, you could use some kind of tree structure with 2 children each. Do we need to use a tree structure? Because we need some way of parsing this to be able to complete the structure, right? So we're gonna have a text file that looks like this. If we look at this, there's actually no space ahead of it, which is nice. But if you try to copy and paste this into a text document, you're going to find that you lose the triangle shape. You're gonna have 1 number on the first line, 2 numbers on the second line, 3 numbers on the third line.
It's a right.
Yeah. We end up with kind of like a right triangle, so we could use a 2D array, keeping track of the current column, and you could either increase or decrease the current column by 1. You could instantiate a tree and read the file and fill out a tree structure with it. That would absolutely work. So first thing we need to figure out how we're going to read it in. And then let's start talking about how are we going to actually parse this to figure out what the maximum path sum is. Any off the top of your head thoughts about how you might figure that out?
What do you mean by the maximum pass? Like how many numbers should they hit?
No, it's the sum of the numbers that it hits, because every possible path from the top to the bottom is going to be the same length. So we could do 3, 7, 2, 8. We could do 3, 7, 2, 5. We could do 3, 7, 4, 5. We could do 3, 7, 4, 9. We could do 3, 4, 4, 5. We could do 3, 4, 4, 9. We could do 3, 4, 6, 9. Or we could do 3, 4, 6, 3. So which one of those sums is the largest? And the answer is 3, 7, 4, 9. First of all, how many possible paths are there through this small triangle? Yeah, we're either gonna, for each place, we can either explore a left child or a right child. So if the tree is just this big, there are 2 of them. If the tree is this big, when you go left, there are 2 possibilities. When you go right, there are 2 possibilities. So 2 plus 2 is 4. So if this is 4 and this is 4, then when you add this to that, you have 4 plus 4 is 8. So there's going to be a power of 2 for each new row that you add. So how many rows? $15 rows. What is 2 to the 15th? It's surprisingly not that large. 2 to the 10th is 1024. So something like that, yeah. So if a computer is able to do, if we're able to do something like in the order of tens to hundreds of millions of these per second, this is something that we could brute force. We could look at every possible avenue here and expect our program to finish in a reasonable period of time. I love how it says in problem 67, the same challenge with a triangle containing 100 rows. What is 2 to the 100th? A lot bigger. That's probably where we need to stop. But we could consider actually breaking this down. So 2 to the 100th is 2 to the 90th times 1024, which is 2 to the 80th times 1024. So I'm going to shorthand this a little bit so that we can do some base 10 arithmetic on this. We're going to pretend like these are 1000. It's going to be slightly more than 1000 to the 10th. So let's actually do that. We're going to raise 1000 to the 10th power, which is just adding 3 zeros every time we do this. So we need to, this is once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, 10 times. That number, there are that many possible paths. So 1,000, million, billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion, nonillion. 1 nonillion possible paths through a triangle with 100 rows. Can people visualize how big this is? It is so big. If we're capable of doing 1 billion calculations per second. So we can go through and say, this is 1 million, this is 1 billion. This 0 means 10 seconds. This 0 means 100 seconds, 1000 seconds, 1 million seconds, billion, trillion, quadrillion, quintillion, 1 sextillion seconds. Anyone want to calculate how many years 1 sextillion seconds is?
Lot.
We could probably just shorthand this with more time than the Earth has left to live. So with modern hardware, we would not be able to solve that problem brute force in the time the Earth has left. And yet, if we use an algorithmic technique, we can reduce all of that time that the Earth has left, plus more, down to less than a second. This is why we study algorithms. For those of you who haven't quite taken algorithms yet, I'm assuming most of you have not taken algorithms yet, right? You'll learn about the technique that will allow you to solve this in under a second. But you can see the power as problems expand in size, the difference between a solution and a good solution to something. So we don't want to solve it like this, but it works here. So let's start there. We can start with a brute force solution to this problem, and then we will eventually talk about what the algorithmic technique is, so that when you see it in algorithms, it's not brand new and horribly confusing. Let's go back to where we were. How could we brute force this?
Check every path and add it up.
Check every path and add it up. So how are we storing it? Are we assuming that we're storing this in a 2D array? Are we assuming that we're storing this in a tree structure? All right, so a tree structure would basically just be, where is my eraser? It went somewhere, it's over there. would basically emulate this triangle looking thing. So we would need some object that represents a node. This is going to be a node. We're going to have a value. We're going to have a left child, and we're going to have a right child. So this value would represent this 75. As we do this, we are going to take this left child and right child, and they're going to be references to node objects. So just like we've said before, when you make something but you don't instantiate it, this is just going to be a node reference. The idea is I draw it like an arrow.
Does that mean you can only go down the tree?
Yes. We don't ever need to go back up the tree, right? Once we're keeping track of a total as we go down, there's no reason to go back up. So each of these are also going to be node objects with their associated left node and right, left value and right objects. So in this value, we're going to have 95. In this value, we're going to have 64, and they're going to point on down the tree to their associated left child and right child. So to do this, we would need a tree class and a node class. This is probably more like data structures than it is like design patterns, but you can never get too much experience with this. So a tree is going to have a root node that is the start. So it's going to have some field called a root. So you would declare a node root. You would instantiate that to be whatever this is, however we read that in. And then as you read each new line, you're going to need to keep track of where is that in the associated tree structure. So when you see this, we're going to say root dot left equals new node, where we have a null left pointer and a null right pointer, because they don't point to anything yet. And then we're going to set its value equal to 95. Root dot right will be the next thing. When we go down here, that's going to be this node's left child. This is going to be this node's right child, but also this node's left child. So this is going to point to the same object. And now we can see how we have two different references to the same object. They're called two different names according to this. So maybe we go by students' names, and each of these nodes are named after one of you. So if we had, student 1 dot right and student 2 dot left, it points to the same student. We could create this tree structure by having each student point at two other students in kind of a tree-like structure. And eventually, two people would be pointing at the same person, but one would be using their right hand and one would be using their left hand. So this would be the tree-like structure that does this. Once we did this, what would the associated algorithm look like? Assuming that we have a perfect tree structure that represents this entire tree, how would we parse it? What would that algorithm be called? Have we seen searching algorithms in trees before? It's not a binary search. Has anyone heard of a depth first search before? So basically, what you're going to do is, rather than looking at this in this order, remember that now this is stored in this structure. We want to go all the way down to the bottom, because if we calculate the sum of all of those numbers, that is one possible solution to this, right? So we could basically say We get this plus this plus this plus this plus this plus this plus this, all the way down until the left child of a node is null. Do we agree that 75's left child is not null? It's 95. 95's left child is not null. 17's left child is not null. We get all the way down, 4's left child is null. We know we're at the bottom of the tree. We found what we call a leaf node. There's no children of that node. Great. If we calculated the sum all the way down this path, we'd end up with some value. If we set a maximum that we've seen so far to be 0, this path is guaranteed to have a higher sum than that. So we could calculate the sum of this, store it somewhere. We're gonna pretend like it's, I don't know, 2,800. Definitely not right. It's definitely less than that. We'll pretend like it's 2,800 and it's the best we've seen so far. If from this node, we were able to backtrack to here and note that we don't need to be able to point back upwards to be able to do this if we use recursion. You end the method, you go back to the last place that you were, looking at the last node. If instead, now you make this associated change, the entire sum up to this point is already calculated. So all you need to do now is look at this value compared to that value, subtract this from that, add this to that, and you end up with the new total. And then you can compare the new total to the old total and say, is this better? Yes or no? Then you would backtrack here, having seen both the left child and the right child, you would go back to this place and go down right, down left. And you would calculate that associated path. And you would have stored all of this information as you went along. Then you could calculate this sum. 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 Then you could, and you can see how you end up with kind of this whole meshed triangle. So let's start here and start working on some code. Let's start by making this tree structure. Let's start by thinking about how can this process actually work, and more toward the end of class, let's give it, I don't know, 15, 20 minutes. I can start actually walking through what that recursive procedure might look like.
How do you get into this from the scanner?
So you're going to read this in as a file. So the file is going to look like 75, 95, 64, 17, 47, 82. It's going to look more like a right triangle, like you said earlier. So we can get next int, next int, next int, next int, next int, next int, etc. So if you're building a tree structure as you read it in, you can say something like you have a node. That node's left child is going to be the next integer. That node's right child is going to be the next integer. What structure would we want to use to be able to figure out the next that we want to fill in the left and the right with? We could use a queue. We could also read this into a 2D array and go straight from there, not having to worry about storing it as a tree.
Just from the tree class.
That'll work. I think we should do it that way. Does your tree class have a node class?
Left and right.
Yep.
And then, just use the-
Yeah, that will be perfectly fine for this. So we see the current node. So this is going to tell us what the value of this is. The next two numbers that we read are going to be the left child and the right child of that. The next two numbers we're going to read are going to be the left child and the right child of this node. But then we started a weird looping procedure where if we're going to a new row, then we want the left child and right child to be the next two numbers that we read Otherwise, if it's the next one, we want the right child of what we just did as the last one to be the left child of the current one. Does that make sense? So we need some way of maybe even reading this in line by line. Maybe that would help us. So we could read this as a next line. If you make a scanner dot next line, it'll read it in as a string. So we need to convert that string somehow into the first integer before a space. How could we separate a string by space? That would get us the string version, but there's an even easier way that returns an array. Let's say we call this string s equals, we're gonna just call it scan, whatever the scanner happens to be, dot next line. And we would have an int array, we'll call this nums, equals s dot split. Have you seen that before? On the associated character that creates the split. This would be like the space character. I'm writing an underline there to represent the space. It's not an underline, it's a space. So this would return an integer array that would be the associated. So this will have one number in it. This will have two numbers in it. This will have three numbers in it. So you throw this into a loop that says for each line of the input file, read a line, split the line into an array wherever you see a space, where each element is separated by that space. So we would get the equivalent of, in this case, we have the first time around, nums of 0 is 75. The next time around, nums of 0 equals 95. And nums of 1 equals 64. And again, you don't need to write this. This is just what happens automatically. So you would want, you could say another loop in this point as you go, while some counter variable is less than nums.length, do something. And that would grab each element of this array and allow you to be able to go through the associated logic that says, for the current row of my node structures, fill in left, right. Left is the same as right, new right. Left is the same as right, new right. Go through that process. It'll be the same number as the length of this array.
Then how do I access them?
You would need references, and you would put those references in a queue object.
So you'd have a growing number.
Yep. You could do it in an array list as well, where each element of that array list is a reference to a node.
So the goal is to find all the path and sum all the path up. Right?
Yep.
Okay.
Find the maximum sum of any possible path.
I was like, the other way was a little too easy if you want the biggest path. I was like,
Yeah.
just find the biggest parent to the child.
Does that make sense? Do people feel like they have a place to start? As soon as you get stuck, let me know. But the most important thing is that this whole process and how to get started makes sense. If that's not the case, let me know. For those of you who are remote, you can also post. Send me a private message, something, if anything doesn't make sense.
See what's happening. Especially the street too, it's like,
Mhm.
because you touch every single one of those numbers at least once.
Right. We all seen queues before, know what a queue is and what a queue does?
Just first one for.
Think of it like a line in a grocery store. The first person to get in line is the first person serviced. Imagine how fun a grocery store would be if cash registers were stacks instead of queues. It's a good thing I'm not a politician. I just mess with people for fun. Pass laws. The only way a line can be done now is as a stack, not a queue.
You just have it. Oh my God. When someone new walks up, they're like, hey, hang on.
Yeah. Society would be so much more violent if we had stacks instead of queues.
Jail.
The worst time to go shopping would be right before everybody gets off work.
The best time to go shopping would be like.
How would this
right
affect
after
Black
Black
Friday?
Yeah, no one would wanna go shopping on Black Friday, right?
No.
You get there and then you have to wait until everyone to get there after you checks out. So you want to arrive at just the perfect time, where you're the last person to arrive or close to the last person to arrive, but you can't space that
But
out
then
so
everyone
much.
else has the same idea.
Exactly, so you have that hive mind, so really the first person who shows up is so
Yeah.
you get a cyclical pattern of what you wanna do changes as everybody catches on. You wanna be the outlier regardless of what the outlier is, but everybody wants to be the outlier, so they have a hive mind of wanting to be the outlier, so they're not outliers anymore, so you wanna be the outlier, so that.
Yeah, no one's getting that TV show. No one's getting it.
Yeah, you can mess with society a lot by just changing the associated structure.
Do you have to assign them outside of this?
It should have a field that is the root node. And then, yeah, you'll need to assign what that root is as in the driver program as you're reading the first number from the file.
Can you do that outside?
You do that inside the what? The loop that, yeah. You know, I guess you would want to assign it outside. So you would do something like, you have a special case for assigning the root.
You make that first.
Yeah, you'd make that first. And then basically, at that point, you would go into a loop that says, if there's another line of the file to read, we want to know what line number we are on, so we're gonna make a number of objects that's based on that line number. You're going to throw those into a queue such that you can iterate through everything in the queue and say, pop the thing on the queue, or I guess dequeue the thing in the queue, assign its left and right child. Dequeue the thing, and then whenever you put them here, you're gonna push them to the back of the queue. Or enqueue them to the back of the queue. So you'd end up with something like, you'd have the root.
This should.
When you dequeue the root, you're going to add the next two things from the file, 95 and 64. So you're gonna make that and assign here and assign here. Since you just handled the root, you're gonna DQ the root, and then you're going to NQ 95 and 64 in the queue. You're gonna read the next line, that is 17, 47, 82. And then you're going to, there should be one fewer object in the queue than there is here. For this first object, the 17, you're gonna say, all right, we DQ 95. We're gonna read the first two things, 17 and 47, and that's what's gonna be its left child and right child. Then 95 is DQ'd. 64 moves up, and you're gonna put 17 and 47 on the queue. Then you come here and you say the one remaining number here has to be the right child of this. The left child is the 47 that I just read. So left child is the last thing that I made a right child for. And then the right child of this is going to be the last number of the 82. That's also gonna get put on the queue. And that pops the 64 once you're done with that, because you handled the left and right child with 64. So now you have three things in the queue, and the next line will be four numbers. So you just repeat that logic of setting and making the appropriate nodes for everything line by line. You NQ whenever you read the number, and you DQ as you make each node's left child and right child. Far and away the most challenging problem we've covered so far in this class.
Yeah, I get how it works, but implementing it was.
Writing the code, yep. This is what's gonna separate someone who is a lower division computer science student from someone who is an upper division computer science student, or someone who is ready to go into a coding interview and be able to do something on the fly. At this point, it's really difficult to implement something like this in a reasonable amount of time, but it's important that you start getting experience with it, because by the time you graduate, you'll need to be able to do something like this in a coding interview environment. You'll be sharing your screen. People will be looking at your process as you solve this. That's kind of scary, actually, to be doing that live in front of people who are judging what you are doing and deciding whether to give you an offer or not. But this is kind of what some coding interview questions might look like. Maybe you don't have to code it live, but you should at least be able to describe how you would solve the problem. Some fun logic in here, isn't there? Yep. Since this is a two-dimensional structure, you're probably doing a two-dimensional loop, a loop inside of a loop. To be able to do this for each row, we need to parse that row into a line. For each element of that line, there's something to do. You need to find the associated left and right child of something that's in the queue for each number that you read as you read it. So I'm teaching data structures next quarter. I may actually turn this into a lab in that class. I'm just thinking about it now. It's a really good Q lab. Yeah, combining tree with Q and saying, what I really find to be a difficult thing for undergraduates to do by the time they graduate is you've learned so many tools in isolation. How do you take a problem that you haven't seen before, identify which of the multitude of tools that you've learned about are relevant to this problem, and then implement them in a way that solves the problem that you haven't seen before? That's not really something you do too much unless it's a project in an upper division course. But it's a kind of thinking that is very important to have practice with by the time you graduate. How's it going?
I was just wondering if we were able to, could you just do recursion instead, and then when you're going through each node, just check if the one on the left or the right is larger, and then if it is, you could call the recursion function again, and then add that value, the node like of results.
Yeah, yeah, when we're actually going through the parsing, so all of this is just made to create the tree structure internally. Once we're trying to answer the question and we have the tree structure internally, then absolutely we're going to be using recursion to answer the question of which path is the biggest.
Okay.
Yeah, that's a great point though. It's great to see. Yeah, so we're kind of breaking this down into two big steps. There's the reading it in and internally representing this tree structure from a file into the active memory of the program. And then we need to analyze that structure to be able to answer the question. How much time do we have? We have 10 minutes. We should probably start talking about the associated recursion method. As usual, there's no way we're going to be able to finish this in a single class period, but it gives you something to go work on. Hopefully, it gives you the idea of how to start, how to work on it. These become excellent things like summer projects. If you're looking for something to do to practice coding over the summer, I'm sure you've experienced this at this point. You come back from a summer and you've forgotten everything. If you don't practice coding, the skills just kind of go away. And it takes a long time to get back into it at the start of fall quarter. So this becomes something to really challenge yourself with over the summer to make sure that you don't lose focus, you don't lose the skills that you've been building. But having these kinds of things just around, you should, with the GitHub account that you made for this, you should go upload this to GitHub, go push it once you have a solution, and then go back and document it. And it becomes an important part of a code portfolio. And that way, if a future employer ever says something like, do you have some examples of some things that you coded throughout your undergraduate experience? You can send them a link to your GitHub that will have every project that you've worked on. It'll be fully documented. It can show what you're capable of. It can show the kinds of problems that you had to solve. And they will see how good of a problem solver you are, or how good of a problem solver you've become because of the problems that you've tackled. Some of those will come directly from class. Like I think that you should all upload the projects that use 3 different design patterns. We're going to do 2 of those in this class. That should become part of your code portfolio. Over the summer, think about the kinds of problems that you could solve that you could also add to your code portfolio. As you take upper division computer science courses, think about the different kinds of problems, the different projects that you have in those courses that you can upload to your code portfolio, but start that now so that you have a long history of programs that you've written that you can show potential employers. All right, let's talk recursion. So at some point, we have this internal tree structure. It's fully complete. I don't expect that anybody is quite there yet, but we can just imagine that we are there so we can talk about where to go next. Once it's together, we want to find all of these paths via a depth-first search. What does a depth-first search mean in terms of recursion, though? So it means basically, for each node, we're going to explore the left node and just kind of start that process. We're going to go to its left child. Once we return from that process, once the recursion comes back to us, then we are going to go down the right child. how do we know that we have a particular sum value? I guess first, how do we want to start? Let's talk about the method itself. So somewhere, I'm gonna need a little bit of room here, so I'll just make myself some room. We're gonna have some calculate sums method. So calculate sums, that's gonna be recursive. It can also be called find largest sum, find greatest path, largest sum, doesn't matter what it's called really. But what parameter or parameters should it take to be able to do this? So one, this is recursive. So you can think about coming somewhere and being in a particular position. Yeah, so basically we can assume that we're starting right here at the very beginning. But it should be the same process regardless of where you're starting. Doesn't matter where you're starting. There's kind of a subtree to this, right? So we could be starting in any particular position. Yeah. Yeah, so we're gonna recursively call the left, recursively call the right. For sure. We should probably check to make sure its children are null first. But the very first thing we should think about is what does this function need to be able to process this? What do we need access to?
Is it just the head node?
We need some node. We'd either call it current, the current one that we're on. And then I could argue that we probably need two more things. By the time we hit a leaf, what do we want to do? Before we return, we need to do a couple of comparisons. We need to, one, know what the current sum is of the path that we follow. So somehow, by the time we get to that point, we need to have kept track of the sum. So I'm going to call this int sum so far. So that way, when we start this process, sum so far is 0. When we are here, sum so far is whatever path we did to get there, and then we just have to calculate the rest of it. So we're breaking this down into the part that we've seen so far and the part that we're going to continue to calculate. Finally, we probably need something that is the best sum that we've seen so far. So the best complete sum all the way at the bottom of the tree, such that when we hit a root, we'll have a current sum. And we want to check whether that's bigger or smaller than the best sum that we've seen so far. By the end of this entire process, when we return best sum from this whole thing, that's going to tell us what the answer is. Make sense? All right, let's start writing. Let's think about what we need. Assuming we're starting at the very top. So before we come into here, we're going to set that the first time we call it, sum so far will be 0, best sum will be 0. We haven't seen anything yet. Starting at this 75, how do we want to proceed?
Sum so far, this equals paired up, data is paired up.
So we first want to, we want to call calculate sums on the left-hand side.
Sum so far.
Yeah, so the current is going to be, so where is the left child of the current node? Because the new current is going to be the current's left child, right? When we want to move to the next part of the depth first search, we want to look at the 95 rather than the 75. It's the 75's left child. So this current is whatever you call this field in the node, you'd have a node object that has a node left, an int val, and a node right. So cur dot left is going to say, follow this reference to this node object. So that's going to be the new cur is the old cur dot left. How does the sum so far change? You're going to add the current value, the value of the current node, to the sum so far. Then, what's the last one? What is the best sum? Does that change?
Yes, because
It doesn't, because we're not in a leaf. So we can just calculate and just pass along best sum. This is wrong. Why?
I think if you do it that way, it's only gonna follow that left path, right? Or it's not gonna.
Yeah, we're not complete yet, but I would argue even what we have here is going to produce a null pointer exception. We're making a very big assumption about this tree, or about the current node. We're making the assumption that it has a left child. When we get down to this leaf, we're basically already saying cur dot left. We're not checking to make sure there is a cur dot left before we do it. We're just assuming that there is. There's going to be an if statement that goes right before this. Yes, we basically want to say if we're in a leaf, how do we handle this logic? I first wanted to go through the recursive logic though, to show you what the recursion looks like, because after we get back from this, we want to call calculate sum on the right child. So we would say cur dot right, sum so far plus cur dot val. Do note though that when you come back, you're going to have the original sum so far. So we're kind of deleting as we forget the path that we've come down. So same thing, same thing. Blah, 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 blah. What does this if statement look like? Yeah, we want to say if cur dot left is null. Notice how we're never going to have a left that's null where the right is not also null. So you could also say if cur dot right is null. Just by the shape of this triangle, you're making that particular assumption. You could also say if cur dot left is null and cur dot right is null. Any of those would work. We're just going to check the left for now because we know this is the state of this. If that's true, what do we want to do?
return to the previous, parent node.
We want to check sum so far.
Turn math.max so far, and best sum.
Yep. Yep, we want to return the maximum of the current path that we're down and the maximum path that we've seen so far. And then by the time this propagates all the way back, by the time this original call returns, whoa, that was fun. By the time this original thing returns, we will have looked at every possible path in this triangle. And in best sum, when we return from that, is going to be the best sum from all of this. We'll have seen everything, every possible path. So this will be the, if we're a leaf, return this logic. Otherwise, look at the left child and the right child. So this turns into a very recursive problem. We're unfortunately out of time. I got through about what I wanted to. It'd be nice to have a little bit more time for this, but hopefully this at least gives you the intuition and the ideas so that you can start to implement the intuition behind this as code. I would like to eventually do something like finish this off and show you the completed program. So maybe someone implements it and lets us know so that I can share it. I don't have time to implement it myself, unfortunately, but
I got a small tree though.
Good.
Yeah, I got the tree and I got the first loop that makes the integers.
this solution will not work as this explodes. So we can absolutely talk about why that's the case later.
Everything, I can't.
Yeah, let me show you how to do that real quick. I'm gonna disconnect from Zoom, and then I can show it to you. See everyone tomorrow.
So you said 1:30?
Yes. And I do have to run to my office by 1.
Okay, so I'll be there.
Yeah, sounds good.